Well, good evening and welcome to the second Quadrivic Mathematics meeting of Book the Second. Today we have with us Daniel Jones and Chris Garcia. I'll turn it over to them.
Thanks, Kathy. And we have Bill Stutzman.
Yeah, Stutzman, that's right.
Stutzman,
Nice
okay.
to be
Bill
here.
Stutzman. Yeah, thank you. So let's jump in. Book the first we finished last time. Like we talked about before, that was the foundation for all of mathematics. So I say that, but really the foundation for all of mathematics is both book the first and book the second. You need both books. Book the first is all about sets. Book the second is all about relationships. I will disclose that Chris and I talked for an hour or two about 2 weeks ago, and we were able to, I think, simplify book the second even further, which was really exciting for both of us. So he'll be talking about some of those things. But relationships, sets and relationships, but I'll talk about in the context of relationships. The way this is written is it's meant to be applicable to relationships of any kind in mathematics. So when you think relationships in mathematics, there's several things that can come to mind. You could be thinking about t-tables, those are relationships. You can be talking about graphs, those are relationships. So graphs are huge in mathematics, as you know. All the things in calculus is all about relationships upon relationships with derivatives and that kind of thing. But it also gets into some of the more fundamental things that most people don't think about when they think about relationships. And if you think about the quadrivium, let me define that for you real quick. The quadrivium is, I think of it as like a box, like a box like this, okay? Where you have arithmetic on the left and geometry on the right. And from top to bottom, below geometry, you have astronomy. And then below arithmetic, you have music. And you might be wondering, of course, most people ask this question, well, why those subjects in particular? The reason that arithmetic and geometry are there is because those are the two mathematical studies that help, like we've talked about before in these meetings, they describe reality. Arithmetic talks about the how many of something, whereas geometry talks about the how much of something, okay? And we'll probably have to get into more detail when we get into book to the third. But for now, just know that that's why the quadrivium exists. They wanted to distinguish between the how much and the how many. And that's the distinction that's been lost in modern mathematics. Because Bill asked a question last week. He said, what's different about this? Because you're going to use language in all of mathematics anyway. What makes language in this context different than language that you would use in modern mathematics? The distinction is that we are trying to define our terms 100% of the time. Modern mathematics doesn't do that. In fact, they can't do that because in the 19th century, they walked away from the quadrivium. Since the quadrivium expresses reality and modern mathematics has walked away from the quadrivium, therefore modern mathematics has walked away from reality, which means they actually can't define their terms. And we talked about that a little bit last week with the fact that mathematicians don't know what a set is, if you recall. And so what we're trying to do is get to the bottom of what all these things are in mathematics so we can actually define our terms. And I bring that up because when talking about relationships in particular, we haven't even gotten to arithmetic and geometry. That's coming up later. The idea of relationships can apply to even arithmetic, the way the ancients applied relationships to music. For example, in music, we have like thirds and fourths and fifths, right? What they're trying to do is make a relationship between number. And that foundation of relationship between number gives us the language by which we can define constructs such as integer and fractions and rational numbers. I'm going to call them rationales because we're not going to refer to them as numbers. And so the point of book the second in terms of relationships is to give us the language by which we can describe those things, the musical nature of mathematics, which is which is integers and fractions and such, okay? But it also gives us the same language by which we can define things that we see more commonly in algebra class, like graphs and that kind of thing. So this common language, this common way of expressing these things is what really is the purpose of books 1 and 2. Give us a unifying theory, let's put it that way, a unifying theory by which we can express all of mathematics and all of relationships in mathematics. So that's the purpose of book 2, just to get us started with that. Any questions on that so far before we get started? Or Chris, you have anything to say?
I think you summed it up pretty well. It'll become pretty apparent as we jump in here, I think right out the gate.
Okay, then let's do it. So let's move on to book the second. We've got our documents in the chat here. We're going to read from the shorter version, which doesn't have some of the pictures in them. Oh, yeah, and Chris also has his screen. Are we going to put that on the big screen? Want to do that right now, maybe? What do you think?
Yeah, we can. We know how the sizing on it is. I've got it crammed in on one screen.
Can we what I mean is, can we get there we go, screen sharing. That's it.
How's
Okay.
the sizing on that? Do we need it wider?
I don't think so. It looks pretty good.
Seems good. Yeah.
Or actually, what I can probably do now that my Zoom is a tiny little box, I can do it like that.
Yeah, that's good. That's good.
Cool. And I'm actually just going to get rid of this. We can spill over if we need to.
So book the second is a unifying theory by which we can describe all types of relationships in mathematics. That's a summary of what I was trying to say at the beginning. Bill, do you want to be our reader today? Okay. So just
Yes,
read
I would be
slow.
happy to.
Read slow like we did last time, and Chris, chime in when you can. Okay.
Okay, and just let me know when you want me to pause. Here we go.
Okay.
Book the second. Let the following be defined. First, a relation is a predicate that is said of one thing with respect to another. If that
Yeah,
which
I
is
think
said,
we might
what's that?
want to stop right there.
Okay, all right, perfect.
Yeah, thank you. Here, I'm gonna get this jotted down on the board. And then so when we were talking last week, something that changed was we kind of relations were constructed kind of separately from predicates. But while chatting, me and Jones realized that we could define relations as a predicate. And so that would then allow us to still keep we're calling these postulates or predicates, or axioms, I mean. I'm looking here for the old ones. Basically let us trim down the number of postulates that we were using. And so I want to just substitute the definition of predicate in here to help us keep track. So a predicate is that which can be said of a thing. So if we were to substitute this over here, then we could say, first, a relation is, instead of a predicate, that which can be said of a thing that is said of one thing with respect to another. I'll let you keep going from here. We'll flesh it out.
Okay, so first, a relation is that which can be said of a thing that is said of one thing with respect to another. Very good. Okay. Moving on then. If that which is said of one thing with respect to another is true, then the other is said to be an object of the relation, and the relation is thus said to be predicated of the first with respect to the second.
Awesome. Okay. Put that in here. Okay, so this is another one of those kind of repeating patterns, which thought I had old notes for this, but I'll have to remake them. So I'm going to bring this back over from our original definition of a predicate. So this book really nicely parallels what happens in book one, where we define what a relation is. I'll put this in blue. So first, relation is a predicate that said one thing with respect to another. And then over for predicate, a predicate is that which can be said of a thing. And then we have a qualification placed on that. if that which is said of a thing is true, then the thing is said to be a subject of the predicate, and the predicate is thus said to be predicated of that thing. And so similarly over here, if that which is said of one thing with respect to another is true, then the other is said to be an object of the relation, and the relation is thus said to be predicated of the first with respect to the second. So it's a very similar construct.
He's showing the parallelism of language, right? The language in book 1 and the language in book 2 are almost identical, just taking words and replacing them with other words.
Yes.
That's part of the whole point of the book. It's supposed to be poetic, right? It's supposed to be this rhythm and repetition that goes through the entire piece.
Yeah. So instead of being the thing, we'll say being one more than. Can be said of the thing with respect to like another thing. Instead of being one more than, we'll say like
How about being greater than, or being bigger than, or something?
Yeah, larger than.
There you go.
So this is kind of our taking the known to understand the unknown. So it's a predicate. So if that which is said of one thing, so this is one thing with respect to another thing.
So being larger than can be said of the object on the right with respect to the object on the left, is what we're saying. And that's the foundation for all of relationships right there. That definition is it.
So this is.
Chris, can I talk about some other examples as you're?
Yes.
So yeah, and I've already described some examples of relationships in mathematics, like graphs and equations in algebra, and then number ratios to give you integers and fractions in arithmetic. This idea of relationships, Kathy, is not only exclusive to mathematics. It's meant to apply to anything in life. So, like his example, being larger than, that doesn't have to be a mathematical idea, right? So, or being older than, like I am older than Chris. So being older than can be said of Jones with respect to Chris, or even being married to, or even being the cousin of, right? Or being the teacher of, right? So being a teacher of can be said of Jones with respect to Chris, because Jones is the teacher of Chris. At least he was before, right? So all the different relationships you can think of in life, because they all work for this definition, what that means is that we're actually stealing from our actual real life experience in our definitions of mathematics, thus fixing mathematics upon our intuition as human beings, which is the whole theme of this entire project. Does that make sense, Kathy?
Yep.
Chris, Bill, you want to speak to that at all?
No, but I think maybe it's a question or an observation that I think is that I would love to hear your thoughts on. I think it'll become evident, but we tend, in English at least, to read of relationship from left to right. And although this is laid out from left to right, the relational elements prioritizes a right to left in terms of the way we think of it. So it's backwards according to the way we would normally interact with it.
We are so glad you brought that up, aren't we, Chris?
Yes, that is something we flagged as a potential pitfall further down. I don't know. I've kind of been thinking of it as like a Western Hemisphere quirk, because you wouldn't really have that if your written language system was right to left instead of left to right.
It's true.
Also,
so
just
in Japan or Israel, we'll be fine.
Mm-hmm.
Yeah. So at what point should we dive into that, Chris? Just to show where, because in mathematics, actually mathematics isn't consistent within itself. I guess that's what we're right now. So ratios as number pairs are written from left to right, like 3 to 4, or 1 to 2. Fractions are also written from left to right, 1/3, 1/3, or top to bottom, 1/3, right? But believe it or not, the XY plane are written from right to left. So anytime you have an ordered pair, like 1 comma 2, and you're going to graph it. Okay, the 1 is actually the these are terms we haven't talked about yet. The 1 is actually the object, and the 2 would be the subject. And we'll talk about that in detail as we go through these definitions. So good observation, Bill.
Yeah.
Thank you.
We'll pick back up on that. I think also with the T tables that we construct, the order is input, output. But
Yeah.
we'll get to that.
Yeah. Any questions, Kathy, so far?
Far I'm tracking.
All right.
Shall I read on?
Yeah.
I'll just go ahead and paste this in as well, just for example.
Okay.
I'm not super pleased with my current diagram here, but we'll pick at it later.
Okay. Second, a relationship is the extension of some relation. Each subject and corresponding object of a relation is said to be an ordered pair of the relationship formed by it, and the relationship is thus said to describe the subject with respect to the object.
Okay. We'll get that in here. And we'll grab an example. And then, so just to
I suppose this next line is also part of this section before we go on to third. So, two relationships that have the same ordered pairs are the same.
yes. Then black. Trying to do blue for supplementary material. Okay, so coming back to like the next parallel. So where we get into the extension of a predicate. This is kind of our arc here. I'll pull this back over. So with the predicate, this is kind of the extension construction. And then we say that the extension of the predicate is the set. But when it comes to relations, it's the extension of the relation is the relationship. And so I'll go ahead and duplicate this. And this is another one of those left to right things where it comes up, if I recall correctly. So our relation we'll say, what did we have up here? Larger than. So this extension becomes the relationship. So that's the form of the relationship here. Is
the relation, Chris, would be is larger than, and the relationship would be being larger than. So it's the same language. So as Chris mentioned, there's some parallelism between books 1 and 2 again.
Right.
So predicate is to set as relation is to relationship. Let me say that one more time. Predicate is to set as relation is to relationship. When we said predicate, we said something like the sky is blue, and the extension would be being blue describes the sky, right? So in this case, a relation, we would say Jones is the teacher of Chris, but the relationship would be being a teacher of Chris. So the relationship would be the extension of the relation, just like the set was the extension of a predicate. Again, a lot of parallels between these two books. They're twin books, books 1 and 2. That's what you're trying to get at, right, Chris?
yes. And then we have here each subject and corresponding object. So in this case, we said up here, object is the thing that actually is larger than. And remember, I think we need to add one more item here. It is that same sort of dynamic. Each subject and corresponding object of its relation is said to be an ordered pair of the relationship formed by it. So being bigger than is the relationship that describes Jupiter with respect to Mars.
Because Jupiter is the subject and Mars would be the object in that case. Jupiter is bigger than Mars. Subject, object, because it's true. Kathy, does that make sense?
Yep. I see the relation.
Yeah.
Except
I'll keep it simple there.
isn't that backwards in terms mathematically? Isn't Jupiter the object here and Mars the subject?
No, Jupiter is the subject. Jupiter is bigger than Mars, so Mars would be the object. But we would say that Mars is the input if we were to make it into a function. So Mars would be the input and Jupiter would be the output. Is that what you mean?
Yes, I do, I believe, because I think below, but I could be mixing it up. So maybe we'll get there. I had thought that the
I have
output,
this backwards.
You got it right.
Okay.
Jupiter is the subject, so that's actually the output.
yes, but I think in the next paragraph, yeah, I think you're right. I think you're right. We'll get there in that next paragraph. But yes, and that makes
Yes.
sense the way we read it in language.
Yeah.
This-
So if you're looking at the T table though, whenever you see a T table, if you're going to read it in English, you have to say it from right to left. Okay.
Right. Yep.
So what we're going to say is that if Jupiter is bigger than Mars, then Jupiter goes on the right. Jupiter is bigger than Mars, because that is the output, the thing that you want to know what is bigger. Jupiter is bigger, so that's the output. Bigger than what? Mars. Mars is the input. You plug in Mars, out comes Jupiter.
Yeah.
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 Yeah,
It's a
but
quirk.
This swap happens.
It's
That
a
was the
quirk of-
swap I was thinking of. Yeah.
There you go. Go ahead, Kathy.
could you say Mars is smaller than Jupiter?
Yes. That actually is called the inverse relationship.
Okay.
So being larger than is a relationship. The inverse of being larger than is being smaller than.
One of the quirks of us as humans when we write these like T tables, right? The way I kind of think of it is almost like whatever the relationship is, right? As far as the input output, I almost think of it as a chronological thing. So like being bigger than, it's like we're interested with the input and the output. So if being bigger than, if we said it was like being bigger than, or we'll get to it down there. But like if this was just like, I'll go ahead and do it now, like y equals to x plus 1, right? And this was the example we were using before,
Oh yeah, good example.
right? The 5 and the 6. So y equals x plus 1 is going to be, we can think of that as being one more than. And so I have the 5 and the 6 here. So this becomes x and this becomes y. Input, output. And so 6 is one more than 5. But if we were going to read this from left to right, like, linguistically, like with language, we would say like 5 is one less than 6. But when we are expressing it in the table, we do this swap. And it's just one of those unconscious things that we do. It's like one of those weird quirks, I think, kind of our language. Like when we are describing an object, like we say it is the big brown dresser. We do size, color, and then the thing. It just feels weird to say that it's the brown big dresser. it's not an explicit rule, but it's just kind of something that we do. So it's like that sort of a thing. Yeah, totally weird, right? It's like it's just an intuited, unconscious rule. So this swap that we do is just something that we do.
Well, and in your example, many foreign languages, the Romance languages in
Yeah.
particular, do that very thing, putting the adjectives after the noun that they're describing.
Bill,
Yeah.
I was just thinking that I'm studying French, and that's, if you're going to say the son of someone, you put it around.
Syntax.
Yeah.
Yeah. So keep that in the back of your head. That'll make this next section make a lot more sense. Or I guess we didn't even talk about this. Okay, so we talked about subject, object, the relationship formed by is said to describe the subject with respect to the object. I think we're pretty clear on that. This is a good example, and we've kind of hashed that out here. And then two relationships that have the same ordered pairs are the same. And then kind of once again, that old thing we flagged, right? Sameness is not equality. Um, so they have the same ordered pairs, they're the same, but that's not equality quite yet.
This axiom, Chris, parallels an axiom from the previous book. Earlier we said two sets that have the same elements are the same. That should be a postulate 3, axiom 3. Should be down further, I think, because it's way down. Two sets that have the same elements are the same. But here it says two relationships that have the same ordered pairs are the same. In other words, is being bigger than the same as being larger than? Being bigger than, is that the same as being larger than? That's a philosophical question, right? Obviously, they're different because we use different words for them. But if we were to conclude that their ordered pairs would be the same, then mathematically speaking, they're the same relationship. Being bigger than and being larger than are the same relationship if their ordered pairs really are the same. It's like an existential way of defining sameness for relationships. Another way you could think of it is if I say being larger than, and if I say it in Chinese, 比较大, okay? Even though I use different words, if the order pairs are the same, then there's an equivalence between those two relationships. Therefore, we'd use 比较大 to translate is bigger than because they're the same relationship, same ordered pairs. And that's an axiom in mathematics. It's something you have to establish to be true. It's not true unless, I mean, it's true, but it's because it's true that you can state it as a law. Yeah.
And thank you for the reminder that this is why this statement is numbered 4, because
exactly.
It's the fourth axiom in the set.
Yes.
Yeah.
And there are only 4 axioms, by the way. Only 4 are necessary.
Well, we've done our work then.
Mm-hmm. Mm-hmm.
Yeah, I think we can go to the next one.
Okay. Thank you for that. Third, a subject and corresponding object of a relation are respectively said to be the primus and secundus of the ordered pair that they form. The primus of every ordered pair of a relationship is said to be an output of the relationship, and the secundus an input. I don't know if you want ecclesiastical Latin or classical Latin on that.
How you read it is how I usually say it. Is there another way to say it?
I suppose you could be just primus and secundus, but that'd be more just like lazy. So
no, primus and secundus is how I usually say it in my classes for sure. Yeah.
Yeah. So this is exactly what we were talking about here. So we have the subject, right? Which we'll go back to Mars here. I'm going to write it down here again for my own sake. I struggle with this. You should see my notebook. I've got it written like 6 times on the 2 sides of the C table to like keep them straight. Okay. Subject. Subject. Okay. So a subject and corresponding object of a relation are respectively said to be the primus. So primus. So subject is the primus. And then the object, the secundus. Of the ordered pair that they form. So like Mars, Jupiter, 5, 6. Which I guess it would actually be Jupiter, Mars, 6, 5. The primus of every ordered pair of a relationship is said to be an output of the relationship, and the secundus an input. So we already have our input output. And this is how you would kind of visually express that. So yeah, this totally threw me for a loop also when we were going over it. Because I totally had them swapped. But are we
based
clear
on
on go ahead, yes.
Catherine's earlier question, we started with being smaller than, we could flip this entire table. Of course, subject would still be on the right, primus would still be on the right, all of the outputs would still be on the right, but Mars and Jupiter 5 and 6 would be switched if what we were talking about was being smaller than,
Yeah, let's go ahead and do that actually.
or being
Just
one
to
less than. Yeah.
So yeah, these two are going to switch because Mars is smaller than Jupiter, but that's still subject object, which still maps to input output. Give another line here. And so then each of these are going to need to switch.
No,
No, not all of them.
just the Mars, the 5, and the yeah.
There you go.
There you go.
And then I'll go ahead and bring this down so they can be side by side.
Chris was this artistic in class too, back in 10th grade. It was so fun.
I'm a verbal and a visual thinker, so open debate style did wonders for me.
Yep.
Okay, so yeah, here's our side by side.
Mm.
And let me go ahead and I'll put like in black the things that are kind of static. I guess X and Y also going to be static here. And also the position, yeah, the Y, like everything in these two stays the same. It's just the sign changes.
On the right, the subject objects are also black. Yeah.
There you go. And I mean, I guess we still have the swapping dynamic. Okay. So there's our two constructions, which it's actually great because we're about to get into inverses and such. So
Perfectly anticipated.
yeah, this is I'm pleased with that. I feel like these books follow a very natural progression. So it's actually awesome that we're just very naturally taking or going to what's coming up. I think that's a good indication of the way these definitions are sequenced.
I think we need Dale back so we can have more debate.
He sends his apologies, by the way. He looks forward to being here at the next meeting. I don't know. He said if you didn't get his text, let Daniel know that I
Okay.
yeah. So,
Yeah.
shall I read on?
So, yes.
Okay. Fourth, the domain of a relationship is the set that describes all of its inputs and the range its outputs.
Okay. So, this is really us just assigning names to things that are there. So, if this were to continue, right, you could have 4 and 5, and I'll drop these. Well, maybe we'll leave those, and I'll make a copy. We'll do the bigger than. So we'll say like a mouse, dog. We'll say like a rat and a cow. So this theoretically has infinitely many ordered pairs. And so we're literally just adding another. Well, okay, so these correspond to each individual entry, but we would just describe all entries, all inputs as the domain, and all outputs as the range.
That's the domain. Yeah. And for those who do a lot of math, this is very familiar to you, right? We know what the domain and the range is. But again, the point of this is to give a universal, a way to universally describe all of relationships. That's why it applies universally, again, to things like t-tables, but also things like number ratios, which get into integers and fractions really fast. In fact, book 5 is when we start integers.
Yeah. So let's see. Our progression here has been subject, object, and then is it primus secundus, and then input output. And then the collections are now domain and range.
Yep.
Yeah. Okay. I think we could probably keep going.
Okay. Fifth, the inverse of a relationship is the relationship formed by interchanging all the primi and secundi of each of its ordered pairs.
Okay. Something really cool here is I typically intuit that the ordered pairs are given rise by calling out a relationship. You know, like, oh, we like kind of even the way we did this, right? We said being bigger than, and then we started listing ordered pairs where that relationship applies. But the actual construction, like here, right, which I think, like, even if we look back, we see it's actually like the ordered pairs that give rise to the relationships. Where when we interchange all the primi and secundi, right, that makes a new, it makes the inverse of the relationship, which is kind of.
It can get, yeah. So what Chris is saying is, if you were to interchange all the primi and secundi of each of its ordered pairs, you have an inverse relationship even before you've named it. So it's not the naming of the thing that makes something exist, because things exist before you name them. So which comes first, the thing or the name, right? It depends on how you look at it. You can say like, hey, being bigger than, I just named it, and suddenly we have the relationship in our mind. But that relationship exists before the name. So what Chris is pointing out is that It's the relationship formed by interchanging the primum and secundi, which is an ordered pairs. That's going to form a new relationship for which we can give a name, right?
Yeah. And that's just one of those, like, once again, right? The approach of these books is very natural and it's very grounded because that is how we interact with reality. That is how we learn about the world. And relationships, the book two, I think, especially, really gets into that in a really cool way. Yeah, that's just like how our brains are wired. This is just like a fun brain fact. I might be quite slightly off on this. It's like an old fact. But like it's like three-fourths of our brain or something. Most of our brain is dedicated like to language slash like pattern recognition. So this kind of goes hand in hand with that.
Now, a moment ago, Chris, you used the term collection, which was not a term we've defined or introduced, but this is an example of we understood the collection existed, and then you called it a collection, and we understood.
I noticed that too, Bill. And if I can just go back to that, he mentioned the collection of inputs is the domain. So therefore, the domain is being an input. The gerund being an input makes the set of all inputs.
Mm.
So if it is an
Yeah.
input, I just use it as a predicate. This is an input, this is an input, this is an input. So being an input would be the domain.
Being an output would be the range.
Yeah, because being an output is the set that describes all outputs. And again,
Yep.
I use the word describe, right? Being an output describes all outputs, the set that describes all outputs.
Yeah, which is exactly the language that's used for sets.
And a mathematician will appreciate that because mathematicians are always going around saying the set of this, the set of that. And I'm just throwing the word the set that describes as opposed to the set that contains to emphasize the fact that these are linguistic constructs because mathematicians cannot answer the question, what is this thing? Because they don't have the language to describe it. Defining things based on our language gives us a very powerful way by which to, as Chris said, ground our mathematics in reality, which is what's missing in modern mathematics.
Yeah. So we already have an example of an inverse, which we constructed top down, sort of, right? Relationship, relationship. Like we kind of flipped the relationship and then showed all of the ordered pairs. But this definition demonstrates, right, that we could have also swapped like the domain and the range and come up with those inverse relationships that way as well. So if I just move these down there, and then we can keep going.
Good.
All right.
Okay, ready? We're on sixth, I believe.
Yes.
Sixth, a relationship is said to be reflexive if each of its outputs correspond with themselves, symmetric if it is the same as its inverse, and transitive if each output corresponds to everything that its corresponding input corresponds to. Might have to unpack that.
Yeah.
Three new
The
key terms.
example, let's see. So let me think. One of the examples that Jones has is the relationship being the cousin of is symmetric, but not reflexive nor transitive, which I might actually need you to weigh in on this one, Jones,
Sure.
because I struggle with these.
Well, I'm going to ask Kathy to help us out with it. So if I say being a cousin of, just from what you understand, could you tell us why that one's symmetric but not reflexive or transitive, being a cousin of?
It would be part of something. If you're a cousin, you're part of a family.
No.
I'm just
Bill.
telling you what it comes to.
Yeah.
Yeah.
Bill, can you tell us why would being a cousin of be symmetric but not reflexive and not transitive?
think it would be symmetric because if cousin X is related to cousin Y, that relationship is the same in both directions. Cousin Y is the same. I mean, is the relationship between cousin 1 and cousin 2 is that they are both cousins of one another, correct?
Yeah. So if
But
I'm
not, but sorry, what did you say? But it's symmetric, but not what?
not reflexive and not transitive.
Hmm.
Let's do the symmetric first. So if I'm the cousin of Kathy,
Yep,
Kathy's the cousin of me.
correct.
Because the being a cousin of relationship is symmetric by nature.
Yes.
Not all relationships are symmetric, right? Being a father of relationship is not symmetric.
Right.
If I'm the father of my son is not the father of me. Whoa, that just doesn't make any sense. So the being a father of relationship is not symmetric, but being a cousin of is symmetric. So what we now have is language by which we can categorize and describe different relationships. And that's how things work in mathematics as well. So it's the same language for the real world as it would be for mathematics. Kathy, does that make sense?
Yeah, so you could, instead of saying cousin, even though I think cousin is better, you could use sibling.
Exactly.
Being
So
a sibling.
yes, exactly right. Being a sibling of is symmetric, but that one's transitive, which is why I actually chose being a cousin of, because it's one that's not transitive. Because if I'm the sibling of Kathy and Kathy's the sibling of Chris, then I have to be the sibling of Chris, right?
But being a
It's
brother of or being a sister of is not
Right.
the same. So you can do
You can
being
only
a
use sibling.
sibling of is able to be symmetric. Being a sister of is not able to be.
But
oh
couldn't I
yeah,
be, right.
good,
Couldn't I
good,
be
good,
the
good.
cousin? Couldn't I be the cousin of Daniel and the cousin of Bill?
You could be, but it's not transitive because it's only transitive if it works every time. So if I'm the cousin of Kathy on my dad's side, right? But then Chris is the cousin of Kathy on, sorry, I'm the cousin of Kathy on her dad's side, but Chris is the cousin of Kathy on her mom's side. Chris and I are not necessarily related at all.
So what if Chris, Bill, and I are siblings and you're our cousin?
Yeah, so in that case, if we're siblings, if you guys are all siblings,
We're siblings, so we're all on the same
yeah, that would be
side.
so yeah, because being a sibling of relationship is transitive. It always is transitive, unless you're going to talk about like half siblings, which then it starts getting weird. But just talk about you know what you think of when you think of siblings. That relationship is transitive, and it's also symmetric. But I think Bill mentioned this, but the relationship being a brother of is not symmetric,
Right.
right? Because I can be Kathy's brother, but she is not my brother. So it's not symmetric. That's
But
that,
it but it would be between you and I,
no,
or between
no,
you
no,
and
no, no,
me,
no, no, no,
right?
no. No, because a relationship is not defined by one of its ordered pairs. It's defined by all of its
All
ordered
of its
pairs.
ordered pairs.
All of its ordered pairs. It has to work in every single instance for it to
Okay.
be a symmetric relationship.
Gotcha. So it's a different ordered pair to say being a sibling of, like you said, is transitive and symmetric.
Yes.
But being the brother of, if you and I were brothers, and the set was only being the brother of and didn't include if Kathy weren't our sister.
No, 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 no. The being a brother relationship is not symmetric in general.
It can't be in general.
Right. If it's not symmetric in general, we just say it's not symmetric.
Yeah. Okay.
Yeah.
So you're saying being a sibling of relationship is not symmetric?
It is symmetric, but being a
It
brother
is
of is
symmetric.
is not symmetric.
Right. Because if you have a sister, they're not your brother, they're your sister.
Yep.
Okay. So that would be kind of the same.
Like being a
Would look
father.
the same.
Yeah.
Yeah.
In that sense, yes. Being a father of that relationship isn't even transitive, right? Because if I'm the father of my son and my son is the father of his son, that doesn't make me the father of his son. So the being a father relationship is not transitive unless you're referring to fatherhood in a different sense, like our forefathers kind of a thing. It depends on what context you're talking about. But I would say it's not, the being a father relationship is not transitive.
So
Okay.
if you dropped the of, would it be so? Instead of being a father of my son, and you just said being a father.
Gosh, that's such a good question. If you say being a father, you're now talking about a set, not a relationship,
Very good. Okay.
right? Because now we're talking about being a father is a gerund.
Yes.
Sorry, being a father is a gerund,
Being a
right?
father. Yeah.
It's the set of all things that are fathers. But being a father of is that which can be said of one thing with respect to another, as opposed to that which can be said of a thing.
So the of is very key in this relationship distinction.
Language is key. Language is key, and I think Greek in particular, they do a good job of having. I don't remember all the details, but one of my colleagues was telling me at one point that you can tell whether or not it's a relationship just by the form of the word. I don't know if it's declension or conjugation or what.
I guess well, I think verbs are conjugation, and then like
It's
nouns are
The case.
declension.
Yeah, the case. That's right.
Yep.
Whether it's a dative case or that kind of thing, right?
Yeah.
Oh yeah, I think you said that
Genitive.
relationships are genitive case or something like
Yep.
that.
That's right.
Cool. Thank you,
Makes
Bill.
sense.
Mhm.
Okay. How do we feel about this section?
Only
That
done
was fun, but I think I need more clarity still on what precisely we talked about transitive. I just want to look at it really quickly. Transitive, if each output corresponds to everything that its corresponding input corresponds to.
Yeah. So
Different. The symmetric is I think the simplest to understand because
Mhm.
it's like a mirror. It goes both
so
ways.
so for that definition, the first thing you should do is when you see the word output, think of the premise, right?
Mm-hmm.
So the premise is related to everything that its corresponding secondus is related to. So if A is related to B and B is related to C, if it's always true that A is also related to C, then the relationship is transitive because A is related to everything that B is related to.
Mm.
Okay. Am I off on this? Is being bigger than transitive?
What do you guys think?
Or is there a way to construct it, right? Where like A is bigger than B. So A is also bigger, and so if A is bigger than B and B is bigger than C, A is bigger than C, and you could keep going. Can we construct a relationship that would pan out that way, that would chain like that?
Being bigger than does pan out that way.
If each, yes, because the primus is always bigger than its secundus. Oh, sorry, over here. Primus is always bigger than its secundus. And so when this,
The premise is always bigger than all of its secundi are bigger than.
yes,
So
right, because we could have
Jupiter
multiple
is
mappings
bigger than
here.
Mars. That's primus and secundus. But then Mars becomes the primus related to Mercury.
Yes.
Oops.
Yeah,
There we go.
Other way
if
around.
if Jupiter is bigger than Mars, then Jupiter is bigger than everything Mars is bigger than.
Right. That's right.
There we go.
But
Jupiter
it
is bigger
doesn't
than
work with Mars. Like
it
you would
does.
have to you'd have to start from Jupiter down. You couldn't start in the middle and apply it because the
Oh, yeah,
relation wouldn't work.
that's right. Unless you are starting again with Mars. So if Mars is bigger than Mercury and Mercury is bigger than the moon, then we must conclude that Mars is bigger than the moon. Yeah. Yeah. If that's right, Kathy, it has to work in every single case. So if that works for every single ordered pair in the relationship, then you say the relationship is transitive.
Mm.
By the way,
Okay.
being a cousin of is not reflexive.
Because you have to correspond with yourself. You're not a cousin of yourself.
Bingo.
Okay.
I'm not
So
the cousin of myself. Therefore, the cousin of relationship is not reflexive.
like a cheap reflexive relationship would be being the same size as itself,
Yeah.
because everything is the same size. Anything is the same size as itself.
Yeah. Being the same size as is a reflexive relationship. That is correct.
Yeah. Okay.
So once again, sameness is not equality.
Right.
Two things can be the same size and be reflexive in that relationship, but not be the same thing.
Yes.
Yeah.
I mean, depending on
Okay.
how we define size, of course. So volume would be something that things could be a very different shape, but have the same volume.
Mhm.
Being the same volume
Yeah.
could be reflexive, even though the containers might
Is.
be
Yeah.
is reflexive, although the containers in other respects are different.
Yeah.
Okay.
Yeah. Having the same volume as a relationship is reflexive.
Yeah.
That's
Okay.
right. Yeah. So you
We
can
move
see
on.
that these terms that we're defining for mathematics, and these are used a lot. Kathy, these terms we're talking about are used a lot in mathematics. Like every day in a math class, you're going to hear one of these terms, right? But you can see that they work for everyday life too. So the student, right? What the student is going to get out of this is that, oh, okay, math is not divorced from reality. It's not like there's math over here and the rest of the world over here. Because all these relationships and all these definitions, if they're rooted in what in our everyday experience, then the math has to be rooted in our everyday experience. Because when you hear reflexive, like, oh yeah, that's talking about this, and you can apply it to math. So that I think that's the real power in what we're doing is that it again makes that connection. It roots our mathematics in the real world experience that the students already have, so that the unknown is built on the known.
And I
These are
can't help,
things we already know.
yeah.
Go ahead.
Well, I was just gonna say I can't help but take into logic also, and when you do the inverse and the converse and you're doing all these you flip this and you negate that. It's just it all is all in my mind. It's starting to connect as a similar skill set, I guess, that you're applying. So as you apply it in logic, you apply it here as you're thinking of these terms.
Yeah.
So
Like literally just for expediency is what most of these terms are for.
so just to not miss the point that you caught, Daniel, I had said mistakenly being the same size, which was sending me down the set path. And you added being the same size as,
Right.
or being the same volume as. And that key
Yeah.
relationship indicator is part of what separates a set from a relationship.
But they're still so similar,
They're very similar.
which is what Chris pointed out to me, is that he said, Jones, I think relationships or relations are actually just predicates. They're just predicates with respect to something else. And once he showed me that
Yeah.
very recently, we were able to downsize. I think we had 6 axioms. We had a parallel for all the axioms. Now we only have 4. So it's a lot cleaner because they are so similar, right? Being a father of, adding one word of means you're saying it with respect to something else. Good.
Yeah.
Okay.
Seventh.
Find it here. Seventh, an equivalence relationship is a relationship that is reflexive, symmetric, and transitive.
If I can just throw some examples out real quick. Being congruent to is an equivalence relationship. Being equal to is an equivalence relationship. Being the same size as is an equivalence relationship. because they are reflexive, symmetric, and transitive. And in mathematics, again, Kathy, this definition comes up like, again, almost every day, it seems like in math.
Being as cool
Being
as
as
nice
cool as nice
kind
as.
as.
It doesn't have to be mathematics. It
Yeah.
can just be a regular definition, right? I'm talking English. I'm talking
Yep.
English, right? I'm speaking English, but segue into mathematics so easily. For those seventh graders, I think this is really powerful.
Okay. I think we can do
Eighth.
yeah.
Eighth. A relationship is said to be ad unum if all the outputs for any given input are the same, e unum if all the inputs for any given output are the same, and unus ad unum if both.
Oh, and you guys probably already know, but it's the to one from one and the one to one. Which one of the things I've always appreciated about the way Jones words things is he'll basically take the same essence of like a word that we already are familiar with and just kind of put it in something a little bit different so that we can more easily assign our different understanding of it or its definition in this context to that like kind of different word. So like once again, literally like this a unum is literally just serving for our own expediency when having conversations in the context of this work, which is really all any word is. Um, but you get to associate with what you kind of already understand as to one. And so, like we said before, right? If all the outputs for any given input are the same, so if the range, if every output of the range is the same, then right, I kind of imagine this. If you've seen it drawn before, you just have like, well, let's see. So it'd be 2, 1 if all outputs for any given input are the same. Um, so yeah, if everything in the range is the same, and then you have the flip, which is from 1 if all the inputs for any given output are the same. And then 1 to 1 if it's both.
If I can
Yeah.
jump in here. So if Dale was here, I tell him right off the bat, so why do we need this definition? That first thing, ad unum, is a function. Like we hear about function this, function that in mathematics, but nobody seems to know what a function is until you get to college, right? A function is an ad unum relationship by definition, okay? That's the first thing I want to say. The second thing I want to say is that the unus ad unum, that definition is essential for defining equinumerosity. Those who are elementary school teachers know this, that you can have two sets that are equinumerous and know that they're equinumerous without counting them. For example, the pig set, the little pigs, right? You guys know how many pigs there are, right? Of the little pigs, and the Stooges, you guys know how many there are, right? But even if I don't know how many there are, I can make a one-to-one correspondence between them to show that they're equinumerous. So this definition has to precede multitudes, which precedes integers, which is why relationships becomes foundation for mathematics, because it's leading into the whole idea of equinumerosity. And you can't define things like the number 1 or the number 2 without it, which is where we're going with the next book.
So just a graphic that kind of illustrates that.
The first one is ad unum because all of the inputs go to one output. Black doesn't go to two different things. The red circular thing, U-shaped thing doesn't go to two different things, right? And the yellow thing doesn't go to two different things. So it's ad unum. Okay? But that one's not e unum because the blue diamond comes from two different things. Just like if you look at that second relationship there, that one's e unum, but not ad unum, because the yellow pentagon goes to two different things. Therefore, it is not ad unum. It doesn't go to one. Each of its inputs doesn't go to one thing. It's not the case that all the outputs for any given input are the same thing. And
And
the
then
third
one
the
to
third
one.
1 to 1, which means they're equinumerous. So the three little pigs on the left and the three stooges on the right, those two sets, the domain and the range are equinumerous in that case, which we haven't defined yet. That shows up right away in book 3.
Okay.
All right. Ready for ninth?
If we're clear here.
Not
I think
fully
I'm gonna have to
clear.
process that one a little bit.
Yeah, I know. But I don't know if
Okay.
it's going to clear up in seconds. So go ahead.
Do we want to try and do some other examples for from one or to one?
I'm actually stuck on the 2-1 because to me it looks like the outputs are not the same. So how are the outputs the same in the ad unum but not e unum?
For any given input, So you have to pick an input. There's
So
three
it's not
inputs.
So it's not that there's no relationship between these three pairs.
Yeah, we're not saying that all the outputs are the same,
Okay.
or that see, it's not that there can't be two of the same outputs. It's that there can't be two of the same outputs for any given input. So how do I explain that? So
those are 3 different inputs. We're not talking about a relationship here. Is that correct?
It is a relationship, but it's saying so the relationship between this input and this output is true, and the relationship between this input and this output is true. But because these two outputs, or sorry, because these are not two distinct outputs, these represent the one output. So if we were to let me see if there's a good way for me to redraw this.
Do you know how we put the relationship over the whole T chart up there? You know,
Yeah.
there isn't a single relationship over this T.
Oh,
Right. Is that correct?
correct. Yeah. So this kind of goes back to what Dale said last time, that this is like an abstract example for which we could make up a being something. But in this case, like, what would we say?
Right.
Yes, that I can see where Kathy's stuck, right? Because in all the examples we've done so far, we've had like words to go along with it. Then suddenly we're throwing to the teachers. Good, Chris, by the way. Suddenly we're throwing to the teachers an example of relationship. And then we do this as mathematicians all the time because the mathematician doesn't have the being up on top, right? That's something I had to invent, right, in order to root it in our language. But then here's one that looks like it's divorced from our language. So it's like an abstracted example, Kathy. If you want a real world example, I can give you one. So a relationship that is ad unum, one for which all the outputs for any given input are the same. Being having being I would say having a dad of this person, which doesn't make any sense. So if I say like Daniel, right, is not going to have two different fathers. So all the outputs for any given input have to be the same. So if I input person and the output is being the father of, there you go, being the father of, that would be an ad unum relationship. If I got that right. Yeah, being the father of. Yeah, so if I plug in Daniel, who's the father of Daniel? It's just one person. It's not two different people. Yeah, that would be an example of an ad unum relationship, being the father of. There you go. My dad's name is Ralph, R-A-L-P-H. So Ralph would go on the right, right? Because that's the that would be the output or the premise. So Ralph is the father of Daniel, right? So Daniel doesn't have two different fathers, so all the outputs for any given input are the same. All the fathers for any given person are the same. There's only one father.
But there's siblings?
Yes, so right. So put in like Jennifer, that's my sister's name, Jennifer. That's still ad unum because Jennifer still only has one father. It goes 2-1. Every person goes to one father. 2-1. Yeah.
Yeah. So you could say to like specifically scope it. Well,
I'm glad you brought that up, Kathy, because that's a point I would have overlooked, right? Because it's not something that I think about as a mathematician. I do these examples in class, but in this context, I didn't even think about that.
So to match
But it
this chart visually, you could add Bill and James,
There we go.
and Bill only corresponds with James, like the graphic above. But
So
Daniel and Jennifer relate to Ralph.
in this case, Bill would be an only child.
Yes, if this were all of it. But I could put Tamara, and that would be just like yours,
Right,
Daniel. Yeah.
right. So if Bill were the only child, it would look like this. James is the father of Bill. Ralph is the father of Daniel. Ralph's the father of Jennifer. That's an ad unum relationship.
So with the next box over, is it true then that if we reverse it, say those middle symbols, the little purple um, teardrop and the cross could be a mother and a father, for example, pointing back to a child that they are both the parents of?
Yeah, so
so being the parent
being
of.
the parent of, yeah, being the parent of is not good. Being the parent of is not ad unum. It's actually neither. It's neither ad unum or e unum.
So it's not a unum either?
Right, it's not because you can be the parents of two different people.
Oh, so that wouldn't work in my example then.
It works as a
So like,
counterexample.
yeah, you're
Well,
trying to think of one that fits this specific graphic.
but if you had an only child, would it fit?
No, because that means every single parent only has one child. It has to work in every case, remember?
Every case. Okay.
Every case. So
Really, there's only one output.
yeah. Wait, for which one?
For
For
the
any
ad,
input?
for the ad unum to be right. All the outputs for any given input are the same, which means that that input can only have one output.
Yeah, that's what it's saying. But good, Kathy, excellent. But I don't use one because we haven't defined one yet. That's how
Okay.
precise this is. In fact,
Mhm.
it's these relationships that we're going to use to define one. It's so counterintuitive because you want to use words that we know, but this is the foundation for mathematics. One shows up in the next book, and we can define one because we have these constructs without using the word, without using numbers. Even though actually that's one of the reasons why I use Latin, because I don't want to use the word one in the word because we haven't defined one, even though it wouldn't matter because we're not using it as part of the definition. To one.
But I guess in a way, yeah, it's already there.
It's already there. That's right. It's already there. That's why we can define it because it's there.
Okay. I guess I'm just adding on for those of us, language people
Sure.
looking at it, that makes it make more sense. When you say the 2-1, the ad unum, it's because
Yeah.
there is only unum there. I won't say one. There's only unum.
Yeah. Each input has only one output.
Yeah.
That's what you can say. Each input has only one output. But I'm not going to say that because I haven't defined the word one.
Mhm.
Feeling
But I
better
have
about
to,
this one?
but I have defined the word same, so all the outputs for any given input are the same.
Do we feel like we can go to ninth?
You want to try?
Let me give one very, very quick example for unus ad unum. You can simply say having a social security number of. Each person has one number and each number has one person. That would be an unus ad unum relationship, a real world example of it.
Okay.
We won't be giving our personal examples for this one.
No.
All right. Ninth, the composition of two relationships, a first and a second, is the relationship formed by the inputs of the first and the outputs of the second that respectively correspond to the outputs of the first.
Okay. I'm going to pull relation or the example for this, which very succinctly puts it as taking out the middleman, so to speak. So the composition of two relationships, the first and the second, is the relationship formed by the inputs of the first and the outputs of the second that respectively correspond to the outputs of the first. So that respectively correspond to the outputs of the first. So you can think of these right here. These are the middleman. These are the bridge, which is what lets you map them.
So would we say that we experienced this in some form when we were talking about the
Oh,
transitive relationship of Jupiter to Mars to Mercury and so forth to the moon? If we just go Jupiter to Mars to Mercury, Mars is the bridge. Is
Not
that
quite. It's similar, but it's not quite like that. The example I use with my students is something like this. Let's suppose I play for the Minnesota Twins, and let's suppose the Twins wear blue jerseys, right? So it's playing for the team of is the first relationship.
Mhm.
Having a color of is the second relationship. I could say I play for the Twins and the Twins are blue, or I could just say I play for the blue team. It's taking out the middleman, taking out the Twins. Because we often do that when we think about like, hey, I am a Twins fan. Wait, what color are the Twins? Oh, they're wearing blue today. Okay, I'm going for the blue team. We take out the middleman. It's the composition of two relationships. So the new relationship would be playing for the team with the color of.
say that again.
Playing for the team with a color of. With the color of. With the color of, yeah. I play for the Twins. The Twins, the Twins are blue. And when I say the Twins are blue, what I mean is wearing the jersey color of, right? That would be the relationship, wearing the jersey color of. Of. It's relationship, right? And I play for the team of. I play for the team of. There we go. Wearing the jersey color of. Playing for. There we go.
Got it. I play for the team of. So you would have the player and you have the team.
Yep. The player would be the first thing, like that.
Input.
Yeah. And then
And
the
then
Pentagon, the Twins, and the Twins. Yeah.
then you have the player. No, this would still be twins here.
Yep.
So this would be like, well, this would still be twins. And you're saying that they wear a jersey color of blue.
Yep. There you go.
So then you could finally say who plays for the blue team.
So the player would go on the left, and then the blue would go on the right for that last relationship. There you go. That
Which
player's wearing blue.
right. Which I guess, okay, so this is mapping literally one entry. So we can assign this to the blue teardrop and the yellow flag specifically.
Yep.
Oh,
And
that's
so
so
you
cool.
could apply this to pretty much all sports teams.
Mm-hmm.
I guess you could get more specific, and instead of saying, well, no, we wouldn't be able to. So the constraint for saying why this isn't a specific player's name in Twins is because the icons are different.
Right.
So if all these icons, so if we had the blue pentagon repeated here and here, then that would be twins, 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 and each of these would be a unique player on the Twins team.
That's right.
So the reason why we said it's just more generic and it's a player of the Twins is because every row has a unique pair in this specific example.
And the reason that it wouldn't just be player, player, player as a general thing, you'd have to specify it, or else it'd be all the same inputs. Teardrop,
right.
teardrop,
Yeah.
teardrop.
That's right.
Well, actually, say this is like teams player one.
Yeah.
Or Twins player one, I mean. And then this could be like Fresno State player one.
Mm-hmm.
There you go. Yeah. Because otherwise, all of the blue pentagons would have to be the same if you went just down Twins players. Yeah.
Red. Yeah. Because the Bulldogs are red.
Mm-hmm. I say, like I was all that interested in sports,
Mm-hmm.
which I wasn't very.
Wait, so you'd probably put, oh yeah, it is Fresno State. Yeah. I was going to say, those are the same. So Bulldogs, Bulldogs, or Fresno State, however you want to identify.
Yeah.
It's a little bit, but not quite like an enthymeme in rhetoric, in which you drop one of the premises or even the conclusion, but you understand the full syllogism with the two that are there.
Yeah.
Is this
Good.
making sense?
Mm-hmm.
And context, this comes up, I've only ever seen this in like algebra 2, where you have f of g of x. For those math teachers who are watching this, f of g of x would be the composition of two functions. That gives a new function by which you take out the middleman. So f of g of x becomes an h of x. Those who teach math know what I'm talking about. So we're basically giving a definition for that. This is where that definition would fit, so that when you get to it, you know what you're talking about. Remember, class, when we defined composition of functions, we defined it with jersey colors and that kind of thing. Now we're just applying it to math.
Okay.
How are we feeling?
Good.
But
Okay. Do you want to close it out with 10th?
Let's do it. And 10th, a relationship is said to be complete if all of its inputs correspond to all of its outputs under the relationship. A complete relationship from one set to another is said to be the relative product of the first and the second.
Okay. A relationship is said to be complete if all of its inputs correspond to all of its outputs under the relationship.
Isn't this called a permutation? Maybe? No.
Okay.
I think it is called a permutation. In probability, this is referred to as a permutation.
So I play for the example here. I see we're using sets here.
We're using sets because the inputs is the domain, right? So you have the domain set, which is set A. The range set is
Right.
set B. If every single if the red pentagon is related to all three elements in set B, which you can see it does. And then if yellow relates to all three, and if black relates to all three, that relationship is complete. Not all relationships are complete. being a father of is definitely not complete because I'm not the father of everybody in the world.
I see. So this is the main. This is the
Most
range.
relationships are not complete, right? This is like a specific type of relationship that's complete.
Okay.
Is it also, if you were to rearrange this, could you say that I don't think you'd be able to say it's symmetric, but if you made the inverse of this and rearranged it so you had 3 blue diamonds,
Mm-hmm.
Oh, so
right? And your 3 blue diamonds would then correspond to each of your red pentagon, yellow shield, and black pentagon. You would have the same complete set, would you not?
It would be the inverse complete set.
Okay.
And actually, you're on the right track because the context in which this definition was created, I didn't create this definition. This is a standard definition in relationships, is in the context of the Cartesian coordinate system,
Okay.
right? If I have a graph, right, that graph is a complete relationship. 1,
Yeah.
1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 3. All those ordered pairs of numbers are ordered pairs of the complete relationship that the graph forms. That's like the bread and butter example because that's the context in which this definition was introduced into mathematics. We need a complete relationship, and we usually refer to it as like R cross R. The real numbers times the relative product, because that's what we're talking about here. The real numbers times the real numbers is the complete relationship that the graph represents. I know it's like a lot of detail suddenly, but I know we're probably really tired too because it's 8:30 or 6:30 for you guys, I think.
Still late.
9:30 over here.
9:30, okay. But yeah, see how I did all those hashings. The black relates to all three, the yellow relates to all three.
Yeah,
That's
this
what
is
I
one of the things a
go ahead.
little harder to see sometimes when you're doing like the relation table, right? Because you have each entry. And so you could have X as 3 entries in it, right? But X is just one input, like this guy here, right? And so kind of reduced it down to like I feel like it's a lot more intuitive this way. This is how
Mhm.
we kind of would see it in the real world.
And that relationship is the relative product of those two sets. That's what this is defining. And again, we need this in order to give meaning to the Cartesian coordinate system. That's why it's there, which is very, very fundamental in mathematics. Yeah.
Great. Thank you.
If I maybe just give one real world example to this, I could say if the set A is human beings, and set B is human beings, being the same species of would be a complete relationship between human beings and human beings, right? Because I'm the same species of every single human being. That'd be a real world example for this.
Can you say that again?
Sure. If set A is a set of all human beings and set B is a set of all human beings, the relationship of being the same species of would be a complete relationship between those two sets.
Gotcha.
Because I am related to every single other human being under being the same species as.
Is that an equivalence relationship?
Yes, it's also an equivalence relationship. Yeah.
Right. Right.
Are all complete relationships equivalence relationships? I assume not.
No, because set A and set B may not be the same set.
So in your
I see.
example, they would have to be in terms of our shapes. If set B was the identical 3 shapes and colors,
Yeah.
then
Then it
that
would,
yeah.
that complete relationship would be an equivalence relationship. That is correct.
So what you just described about being the same species as would be this.
Chris, how do you come up with this? It's so good. Yeah, that would
I'm very I'm very big on reusing things. I feel like it makes it easier to like grow the understanding.
Yeah, so that would be an example of an equivalence relationship that is also complete. Good.
Okay.
Yep.
Lots to contemplate.
And that completes book the second. That is
All
the
right.
fullness of relationships. Yep. Chris, anything you want to close it up with?
I feel like a little slow on a lot of the similar dynamics, like the emergent patterns, like what we had with the set construction to the relationship. We kind of flagged them along the way. I feel like we maybe could have dived a lot deeper into those. Um, Although, I mean, we closed out the book in our session, so that's good. Um, but we'll probably, I think it would be good to come back to some of these just in future books, just to keep a tab on, the sets kind of giving rise to these patterns, and like those same patterns echoing in the relationships, and like kind of each time those dynamics emerge, they're like bigger and bigger constructs. It's just kind of like this echoing, like fractal, as far as the way it gets constructed is. And it's so hard to articulate every time. But I'm gonna keep calling it out because once you start to see it, like you start to see it. It's really cool. Um, yeah,
I agree. I totally agree with that, Chris. Thank you.
yeah.
Bill, any last words?
No, just thank you for that. I do appreciate the correspondence between the set and relationship principles. I think
Yeah.
that is helpful.
Yeah.
Yeah, I agree.
And the of and the as and the of.
Yeah,
Those words.
the genitive form, if you speak Greek.
And just to be clear, because you mentioned this very early on, with arithmetic being focused on how many and geometry focusing on how much, we're all still in the realm. This is the foundations of arithmetic here.
Exactly. Yeah, we are in arithmetic actually.
Yeah.
The how
That's what
many.
this book is,
Yeah, this volume,
or volume, yes.
book the first through book, I think it's gonna be 12 of the first volume is all arithmetic, and that's where we're at. We still have to finish that before we can even start geometry.
Yep.
Because geometry cannot exist without arithmetic, because you can't even talk about an octagon unless you know what the number 8 is.
Sure.
Okay, Kathy.
Okay. Thank you.
Yes, you're so welcome. Thank you everyone for coming tonight.
So see you guys next time for book 3, right?
Lord
Yep.
willing. See you then.
All right, thanks, Kathy. Take care, guys.
Bye.
Okay, I stopped
Did
the recording.